Hello everyone. In previous lectures, we talked about evaluating limits numerically and graphically. In this video session, we're going to be looking at evaluating limits analytically. Okay, so as usual, I'm going to go over the topics. First about the recap and then what you're going to do. So we have talked about the classical calculus problem, the tangent line problem, learned about informal and formal definition of limits, and how to find the limits using numerical and graphical approaches. So in this lecture, we're going to look at the analytical approach. Just a little quick recap of the tangent line problem. So remember, in a tangent line problem, what you're given is a function f and a point P, and you like to find the equation of a tangent line at this point P. If the tangent line is not a vertical tangent line, this problem of the tangent line in calculus basically boils down to saying finding the slope of the tangent line at the point P. So what we normally do is to find the equation of a tangent line, we need is a point and a slope of the tangent line. Now to find the slope, we need another point Q. Remember that we draw a secant line through these points Q and P. And what we have learned all previously is that as this different points Q on the graph of the curve y equals fx approaches the point P, the slopes of these different slopes of the secant lines QP will approach the tangent line, the slope at the tangent line at P. Okay, that's the key point, that the slope of the tangent line to the graph of the function is nothing but the limit of the slopes of the secant lines. A quick example of numerical and graphical approaches. So remember, if we are given a function, say x cubed minus 1 over x minus 1, we want to find out what happens at x equals 1. So we were talking about the numerical approach to this function, x cubed minus 1 over x minus 1. As I repeated earlier, this function, as I said earlier, the function is undefined at x equal to 1, and we want to study what's the behavior of the function near x equals 1. So what we notice is we take values closer to x from either side, on the right and the left, the function is approaching 3. That's just by plugging in the numbers. Then, if you look at from the graphical approach of the same function, we just see the same, that when x is at 1, the function is undefined, is shown in the form of an open circle. And once again, when we are coming from the right or the left when x approaches 3 over here, so that's somewhere here, that's 1 here. So, sorry, at 1 here, the function fx is approaching 3. Sorry, guys. Okay, now the informal definition, which is very important, is one which we'll be using throughout. If the function becomes arbitrarily close to a single number L and x is approaching C from either side of the rod C, then this limit fx as x approaches C is L. This is the main thing for us, guys. The limit of the function fx as x approaches C is L. So we say that when this is working, we say that the limit exists. Okay, now we're going to look at analytic approach. There are different ways of doing it. We'll start with the very easiest, which is called the direct substitution. Now here, the limit of this function fx as x approaches C does not depend on the value of f at x equal to C. It's very important. Remember, in the previous scenario here, when the function was not even defined at x equal to 1, the limit was existing. That is the beauty of this limit approach in calculus. that even though the function is undefined, calculus says, hey, there is a lot of things going on near that point where the function is not defined. That's what limit tells us. He says, limit is saying, hey, hold on, let's see what happens here. In this scenario, notice when x is not defined at 1, but the function is approaching a value L, which is 3 over here, from both directions, right and left. So, now sometimes it happens that this limit is precisely f of c. For example, if I take this nice little graph, I have this line. So I want to find the value at c. Clearly, it is not only defined, but the value of the function is the same as the limit value. Okay. Now, in these cases, we can evaluate the limit by direct substitution. What basically it means is wherever x is going, take that c and plug it in x in the value of the function. Now, this direct substitution property is valid for all polynomials and rational functions with a non-zero denominator. Okay, so that is direct substitution. Let's look at some theorems. And very, very simple theorems, guys. I'm going to draw some pictures and show it to you. And then do examples. So the first theorem is called some basic limits. The first is if b and c are some real numbers and n is a positive integer, then the limit of b, that is the function is just the value b, as x approaches c is b. Now this basically means that the function is a constant. What does that mean? Your graph is a horizontal line. So no matter where you are on the x-axis, the function will always approach b. Now, the second property says the limit of the function fx where is given by x as x approaches c is c. Now this is the classic example y equals x. Now remember this, guys, is y equal fx. Now this means that y equals x. This is a straight line passing through the origin at a 45-degree angle. So no matter where we are going to look at x, the c, wherever you're going to look at x on the horizontal axis c, the value of the function is the same as x, which is c here. Now, if you're looking at some powers, x to the power n, where n is a positive integer. Now, if n is 1, then it is basically the top one. When n is 2, it's a squaring function. X is 3, n is 3, it's a cubic function. The answer is this is a nice little polynomial. You just substitute in place of x a c. So let's do some examples. Now, the limit of the function 7 when x approaches 5. Now remember, the function is a constant. The answer is simply the number itself, that is 7. Now, the limit x approaches minus 3 of the function x. Replace the x by minus 3, where you're looking at. That's number 2. The limit as x approaches minus 2 of the function given by x cubed, which is number 3, which is basically replace x by minus 2. That's minus 2 cubed. The answer is minus 8. Okay, now these are very simple basic limits. Let's look at properties of limits. That's Theorem 1.2. There are quite a handful of them. And as you practice a lot of them, you won't even need to memorize this. It will just become a part of you. So let's go and look at it for the first time, and then as we practice, we will see it. What these properties of limits are saying that if you have two real numbers b and c, and n a positive integer, and we have two functions f and g whose limits are existing. In other words, limit of fx as x approaches c is L, and limit of gx as x approaches c is k. That simply means the limits are existing. The scalar multiple, now the first property says if you take the limit as x approaches c of b times fx, you simply pull the b out and apply the limit, which basically means b limit x approaches c of f of x, which is b times L. Okay, if you're looking at sum and differences, so if you're taking the limit of sum and differences of two functions, it's basically the sum and difference of their limit values, which is L plus minus k. Now when you're looking at a product, if you're looking at a product of two functions and the limit as x approaches c, basically it means you are having the product of their limit values, L times k. In a similar fashion, when you look at the quotient, limit as x approaches c of fx over gx, it's going to be L over k. Very important, k cannot be 0. Remember, the limit should exist. That means the default thing that there should not be a 0 in the denominator is very, very important. And finally, the power property of the limits. Limit as x approaches c of the function to the power n, which simply means because we know the limit value, we replace the limit value and raise it to the power n. So we're going to do some practice of these properties we just have learned. Okay, let's look at this property. Limit of 3x cubed as x approaches minus 2. Now, many things are involved, guys. The first thing is you see a constant multiplied. So we will take the scalar multiple property. We remove the 3 out. That's 3 limit x approaches minus 2 of x cubed. Now remember, this was the one which was our basic limits. So what we're going to do, we are just going to apply, as this is a nice little polynomial, we're going to just apply minus 2 in place of x and raise it to 3. So it's 3 minus 2 to the power 3, which is 3 times minus 8, which is minus 24. Okay, let's look at a next example. So this is sum and difference. So you have two functions and there is sum between these two functions. So we apply the sum or difference properties of limits, which simply means this is going to be limit x approaches minus 2 of 4 plus limit the limit of 3x cubed as x approaches minus 2. Now clearly this right hand side as x approaches minus 2 has been done on the top, so we know that's negative 24, and the limit of 4 as x approaches minus 2. Remember this 4, guys, it's basically the basic limits we talked, limit of a constant function, which is simply the constant function itself, 4, and limit of 3x cubed is x approaches minus 2, which we did on the top, is negative 24. The final answer, negative 20. Okay, now let's look at properties of limits and how they can be used in different ways. So this example is if you are given two functions with limits such that the limit of fx as x approaches c is 2, a limit of gx as x approaches c is minus 6. Now you do not have to worry about what the f's and g's are or what your c is, you just look at the bigger picture here. So the first question is, what is the limit as x approaches c of 5 times fx? Now remember, this is a constant multiplied to a function. We just have learned this property that this is writing as 5 times limit x approaches c of f of x, which is 5 times 2, which is 10. The next property is a combination of the scalar multiple and the difference between two functions. So you can write this as limit of the 5 times fx, x approaches c minus the limit. Remember, it's a constant. This is minus 1 times gx, so minus out x approaches c of g of x. Now the first expression already we have done earlier, which is 10 minus, and limit of gx as x approaches c is minus 6. It's a minus of a minus 6. Your final answer, 10 plus 6 is a 16. Now third, limit of the product of two functions as x approaches c is the same as you are multiplying their limit values as x approaches c times the limit gx as x approaches c. The final answer is 2 times minus 6, which is minus 12. Okay, now let's look at the power rule. Limit as x approaches c of fx to the whole cube. This is basically your limit of the function. This limit of the function fx as x approaches c the whole cube, which is basically 2 cube, which is 8. Remember the limit of the function fx, and we are applying the power rule here. And we can also think of this problem as, this is like fx cube, notice is what? It is fx multiplied 3 times. Okay, the last one, limit of the function fx cube of the x approaches c of the function is fx cubes plus 3 over 2 gx minus 2. Okay, so basically it's a quotient rule first. You apply limit of fx cube and thus plus you will then you will apply plus 3, then you will take the limit in the denominator of 2 times gx minus 2. Then you go inside and apply the limit properties, the limit as x approaches 3 of fx cube plus the limit as x approaches c of 3 over the limit. Now it's 2 times gx, remember, which 2, we can take the 2 out, minus the limit of the constant, which is a minus, sorry, let me take this here. Minus 2. Now the top one, limit of fx cube, x approaches 3, we have already done the math here, it's 8. Limit of a constant function is 3 itself. Now limit of b as x approaches c, so your b is a 3. So limit of 2 times gx is basically 2 times the limit of gx, which is 2 minus 6. Then minus of minus 2, that's the constant. So top is 8 plus 3 is 11, minus 12 plus 2, the final answer is 11 over negative 10. Okay, now let's look at limits of polynomials and rational functions. If we are given a polynomial function p and a real number, then the limit of px as x approaches c is simply p of c. It's basically direct substitution. And if I have a rational function r given by px over qx, c is a real number such that q of c is not 0, then the limit of rx as x approaches c is simply rc or pc over qc. Again, it's direct substitution, and we have just talked about it also earlier, that if you have a function which is a polynomial or a rational function with a non-zero denominator, you simply just apply direct substitution in your limits. So example here, so if you have 3 minus x squared limit as x approaches 5, so basically just apply 5 wherever you see an x. So the answer is 3 minus 5 squared. So it's 3 minus 25. The answer, negative 22. Now the next one, limit as x approaches minus 5 of a rational function x plus 2 over 3. Clearly, there's no problem in the denominator. Just go ahead and plug the values. So it's minus 5 plus 2 over 3, which is minus 3 over 3, which is minus 1. Okay, the last one. The limit as x approaches minus 2 of the function x plus 2 over x minus 1. So make sure you first plug in minus 2 in the denominator. You should not get a 0. So what we see is when you plug the minus 2, you get minus 2 minus x. Awesome, great, don't worry. So you plug in the values, so direct substitution, minus 2 plus 2 over minus 2 minus 1. So the numerator is 0, but the denominator is not 0. That's very important. Minus 3, the final answer is 0. Oh, there's a repetition. Oh, okay, didn't realize. So just cancel this one, guys. Now, Theorem 1.4, these are the limits of radical functions. It says if n is a positive integer, the limit below is valid for all c when n is odd and is valid for c greater than 0 when n is even. So that is the limit as x approaches c of the nth root of x is the same as the nth root of c. Now here, let's look at this. So we are going to example limit x approaches 0 of square root of x plus 4. Now clearly it's a square root function, even function. So when I plug the value 0 in the function, it's happy, it's not a problem. So just go ahead and do that. So it's going to be square root of 4. The answer is 2. Now let's look at the limit of this expression. First of all, it's a cube root function. It's odd. So if you have a negative inside, it will not affect us. It's a negative outside. Remember that. So the limit as x approaches 8 of cube root of negative x squared. So what you're going to do is just simply plug in. It's a cube root and negative is outside. And then it is 8 squared. So which is cube root of negative 64. And we know the answer is negative 4. You can do the math also. You know what is negative 64? Cube root is negative 64 to the power 1/3. And negative 64 is what? Negative 4 cube to the power 1/3. So the 3 and the 3 cancel out. You get negative 4. And that's what we do here. If you want to do mentally, in your head. Okay, let's look at limits of composite functions. If you have two functions, f and g, such that the limit of gx is L as x approaches c, and limit of fx as x approaches L is f of L. Now remember, composite functions means what? That the output of one function becomes the input of the other. So remember, the output of g is L, which becomes the input. So the limit, so this is the function f of g of x. So the output of g becomes the input to f. So there's a limit of, as x approaches c of a composite function, is basically you take the limit inside. So f of limit of x of c of g of x is f of L. Okay, so let's look at an example. We are given two functions g of x, 2x squared minus 3x plus 1, and then a function fx, which is cube root of x plus 6. We would like to find the limit of x approaches 4. It's f of g of x. So it's a composite function. You take the limit inside. So f of limit of g of x is x approaches 4. So you take f limit of 2x squared minus 3x plus 1 as x approaches 4. Now clearly, this is a polynomial. Substitute 4 here, you get 21. It's 2 times 4 squared is what? 2 times 16? 2 times 4 is 6, 2 times 4 squared, that is 2 times 16, that's 32, minus 3 times 4, that's 12, and 1. So it's basically 32 minus 12, which is basically a 20, and then add a 1, 21. Now you take the cube root of 21 plus 6, which is cube root of 27, and we know it is a 3. Because 3 cubed is 27. Now let's look at the limits of trigonometric functions. So if given c a real number in the domain of the given trigonometric functions, so the limit of sine is nothing of sine x as x approaches c is simply direct substitution sine c. Similarly, limit of cosine x as x approaches c is cosine c. Limit of tangent x as x approaches c is tangent c. The limit of cotangent x as x approaches c is cotangent c. And limit of x approaches c of secant x is secant c. And limit of cosecant x as x approaches c is cosecant c. In other words, all direct substitution. So let's do examples. Limit of tangent x as x approaches 0, you simply say tan 0. The answer we all know is 0. Limit as x approaches pi of x times cosine x. Remember, it's a product of two functions. So this is limit of x as x approaches pi times the limit x approaches pi of cosine x. So what you get is pi times cosine pi. Now we all know cosine pi is minus 1, so this is minus pi. So this is minus 1, remember. Now, limit as x approaches 0 of sine square x. Now, this can be the same sine square x is what? It's sine x the whole square. Or we can write this as sine x times sine x. So what is this? This is the limit of x approaches 0, sine x times the limit x approaches 0 of sine x. It's a 0 times 0, which is basically a 0. Cosine of 0 is a 0. Okay, now I have written down some practice problems for you based on what the examples I have done earlier. So there are 3 slides. Go ahead and work on them. And then the next one, the next of the slides, I'll be doing the next session. That is going to be part 2. Thank you.